if I write KVL here? Let's get into KVL here. It says EA is equal to RAIA plus RFIF, right? And because IL is equal to 0, how much is the IA and IF? They are the same, right? So basically, usually we don't care about RA. We can go directly with RF. But in this case, because it's easier, it's more accurate, I'm going to do it this way. So EA is going to be right. RF is 20 and RA is 0.2. We can see here. So basically here it's going to say EA, right? If I would have ignored the drop voltage under resistance, how much would have been EA? 20, right? Now considering the resistance of the drop voltage under armature is at 20.2, right? So how much is it? 0.2 over 20. How much is it? 0.2 over 20. 1%. It's a 1% error. If I wouldn't have considered the 0.2, would be 1% error, right? So my point, you see, is not that big deal. Even you can, because in this case we can put it together. It's easy. But if we have a load, we cannot do that. You know what I'm saying? Because if, for example, we have a load, you cannot say this current is equal to this current anymore. Forget it. Now, what's next? Yeah, draw the wrong, but I don't know where it is. You know, either line is going to be like this, right? Or it's going to be like this, right? I don't know. This one is not the scale, but I put in the board. Let's assume, just I'm guessing. I'm just guessing. Let me go with the wrong guess, and I don't want to go with the right guess. Let me see what the answer. Yeah. Let's say it's going to cross here. Let's say it's going to cross here, right? So let's solve it. So I'm guessing maybe it's going to yes, cross here. So basically I should cross this equation and this equation, right? So let's put it together. As I said, I'm guessing. You know, I'm going to show you my guess is wrong. What is the equation for this part? What is the equation for this one? So let's solve them instead. I went to the right one. And IF. So IF is going to be, no, that's good. So bring this one here, I'll put this one here. It's going to be AD is going to be 79.8 IF is equal to -1, right? So IF is negative, right? IF is going to be something something 1 over 79.8. This is wrong. Why? Current cannot be negative, right? Current cannot be negative. So why this one is wrong? Why this one is wrong? Because my assumption was wrong, right? I said, let's say I assume it's crossing there, it ends up with the wrong answer, right? So we'll go, let's say, okay, so here I was wrong. Let's use this to. Let's use this to see how much we're going to get. So if I use those two, it's going to be the second part equation is this, right? EA is 2IF plus AD, and EA is equal to what? Next one, 20.2IF. So here, 2IF plus AD is going to be 20.2 IF. So IF is going to be 80 over 18.1. Okay, that's that's a positive current. But still we need to check something. See, if I solve this equation, the number comes 0.7. Is it correct or not? No. The current cannot be less than this, right? Because we said it's going to cross here, right? If I come up with something again, 0.7, still again, this, one of them has to work. You know what I'm saying? You select this one, you end up with a negative current. You select this one, you're going to end up with right current. So good. But let's say we started with this one. We didn't know. First time we didn't know which one to start. We started with this one. The current came positive, but come, for example, 0.5. That's wrong, right? Because this equation is not valid for the 0.5, right? So if you solve this one, IF is going to be 4.395, right? How much is the VT? How much is the VT? VT is going to be IF, right? How much was IF? 20 times 4.395, right? How much was the, well, how much is the drop here, if you want to calculate? 0.2 times that number is about 1 volt, 0.8, 0.9 volt, right? So it's a little bit good. If you calculate the VT, you can see that VT is about like 84, 85 volt, right? So you're going to have 1 volt over 85 volt, you know. I'm saying under the no load condition, to assume this one is almost equal to this one is pretty accurate. It's not a very big error, right? So you can see here, this one is about 85, this one is about 86, right? 1 volt difference, you know, it's less, it's about a little bit more than 1% error, right? So these are two simple examples on the separated machine and the shunt machine. Now we are going to go to series excitation. Series excitation. So when we talk about excitation, we said separately excited. So the source was for the field, for the excitation system was independent source, right? We call it shunt excitation. This is why we call it shunt, right? Because this one is parallel with the armature circuit, or we call it self-excitation. That way it's explained what we call it self-excitation. Now we're talking about series excitation. Series excitation is very like this. Again, we have an armature. This is the armature circuit. Either the motor or generator. So where is the excitation system? In series, exactly. In series with the so it could be a motor going this way, it could be a generator going that way. See, this excitation system, usually, you know what I'm saying, they have a specific application, you know. Let me explain, for example, this one, the shunt machine, you know. what is the specific before going to the second series machine. There is a curve in your book. If you go look at it, I think it's VT versus I believe IL, something like that. If you go, you're going to see something like this. If you go look at your book, I'm not going to go through the characteristics a lot, but just I say, when you are talking about all this excitation, they are good for different applications. For example, this one is good for drill. You know, when you are going to drill, I'll tell you why it's good when you use them as a motor, why they are good for to be used as a drill. But here, for example, this is the VT versus I of a shunt machine. I'm not going to say how we're going to get to this curve, but I want to tell you about one application of this one. How many of you are familiar with welding? So, welding, you know, if you look at it, you know, when you do the contact and you start to do the welding, you know, basically you are shorting this. This is electrode, right? And you pass a lot of current through this, you know, electrode, right? And you melt it and you start to do the welding, right? So look at here. What does it mean if VT is 0? Short, right? So if I short here, look at here. Whatever, any source, you have to keep in mind. You have any source. If you short it, what do you expect?
No excitation.
No, I'm saying no, forget this one. Any source, like a battery, like whatever. In general, when you short it, it's a very dangerous thing, right? Yeah, it's going to boom something, right? But here does it. Look at here. If you short it, what's going to happen? The current is self-protected against short circuit. This is a characteristic of this machine. So even if you use the, for example, welding, which you are shorting the terminal of this one with that electrode, so the current is going to go up to something, and it's going to stay at this much. You can use it for welding. So welding is kind of shorting your circuit. You know, if you have this machine, you short here, boom, it's going to go off, right? Because this is source, right? There is no limitation here. But over there is a limitation. Why? Because when you short here, think about it. The current here is going to reduce, right? So basically, automatically, it's going to bring the voltage down in this curve, right? Automatically, how you can protect against short circuit? If you can bring your voltage down, the short circuit is going to go away, right? So basically, it's going to automatically go adjust it, and somewhere it's going to give you some current, right? It's not unlimited current to fuel your machine, right? So I'm saying this thing we are saying, say series excitation, self-excitation, shunt excitation, they have different applications. The most common one is separate excitation. You can use it for motors, you can use it for generators, but it is a specific application, for example, like welding, like drilling. You know, drilling, I'll show you why this series machine is very good for that one. Based on a specific application, you can go select different excitation. But here, just I'm giving you all this kind of things. If, for example, if you read in the book, it says, okay, we have this drill is series excited. So at least you can go look at, okay, what does it mean when this is series excited? So the circuit is this. So the torque equation is this. Oh, I understand why it said they're using series excitation. My point here is I'm going to this is like a circuit we're introducing, but each of them, they have their own application, you know, where to be used. Now, let's go through the series excitation. Again, if you want to write it, for example, for the generator case, if you want to write it, it's like this, right? Because this one is not used as a generator, I'm not going to focus very much on it. I'm going to switch to the motor. This one is mostly, the shunt is most of the time is used as a generator. I didn't talk about the motor case anymore, but you can do it yourself again, like a separately excited machine. But this one is mostly used as a motor. I'm going to quickly talk about the generator case. So for the only equation here we have, EA is going to be RA plus RF, IA, right? Because IF and IA, they are the same, right? RF and IA, they are the same. Plus 2 VB, if there is a drop voltage here, plus V. This is the equation for the generator case for this self-excitation machine. But in reality, because you know for the control, you have to change the field, right? One way was to control the field, to control the machine was to changing the field. Here we cannot change this one, because this is in series. You cannot make it very hard. What they do for control purposes is like this. They have this RALA, and they have this RFLF. Let's just forget the L. Make it simple. Okay, put it this way. So basically, by change, could be a real stuff. I'm not sure if you have it in the lab or not. If you have a series machine, and you want to change the field. So you can, because these machines, they have an internal structure. You know, we talked about that one. They are showing one over there. You cannot change that one anymore. As for when you build the machine, you cannot touch that one anymore, right? For example, this machine, usually in the lab, it tells you, so there is a armature connector, for example, give you, I don't know, A1 and A2. Basically, it's giving you these 2 points. From here, right? Because RA is also part of armature, right? And it gives you, for example, 2 here is a F1 and F2, for example. F1 and F2. Here between these two there is this. And here you have this one. This is the excitation, right? Now this is what is built in the machine. And this is only for the lab. Usually in the machines in the lab you have this kind of thing. This collection usually give you this one. Usually the exhaust they are built in and you're not going to touch them. Now, if you're going to change the current here, this is fixed. You cannot go inside the machine, change the winding. But what you can do, you can put another stud here, right? Right? You can put that one. You can connect this one with a wire here. Now, see? This is your circuit, right? So you can go change this one. If you change this one, you can change the current in the field winding, right? I'm saying, you're going to see most of this thing in the lab. The good thing is when you go to the lab this week, you know, you'll see lots of this thing in the lab. So you have to do the connection yourself. But before running the system, this is the rule for the order is going to tell you. You are not allowed to run the system until it comes and check your wire, because that's very dangerous, you know. Easily it can cause lots of problems. You know, this is a 110 volt, those kind of things, not low voltage anymore, you know. You finish your circuit, and it will run down, you know, and you're going to come quickly check to make sure your connection is correct, and you can run your system. Hopefully it follows that rule, because when you're at this thing, you know, I have told him to do that, and I'm sure he's going to, but when I was a student, he has to come check it. Before he comes, you know, we were not allowed to run. And that one was really big electric machine lab, you know. So but my point is, now you have these 2 points, and you have these 2 points. You cannot change this one. You cannot change this value, right? But you can put the external resistor here and change it. You know. Now let's look at this one as a motor. You know, as I say, this one is not used that much as a generator. If you want to write the equation again, you know, full equation here. Let me write the full equation here, for example. So how much is the IF here? This is the IF, right? And this is the IA. That was a simple case. There is no resistor. But here we have IF and we have IA. So IF, this is a current sharing here, right? This one is IA, right? The current coming here is IA, right? How much is going to go here? Right? That's IF. The current sharing between 2 resistors, right? So how much is the IA? IA